Okay, we'll start now. Actually, so today's class, actually, we are going to have the demonstration of this linear regression we discussed in that previous class. So, quick recap, right? So, the parameter we are talking about, right? So, W transpose phi of x plus epsilon. This is the model what we are talking about. So, in this, we are trying to get this relationship, right? So your y of x that is equal to W transpose phi of x. That is the regression model. And what you observe is a noisy one. T is basically the noisy here. But extending the problem to the vector is not a big issue. Problem separately, right? So we are this expression actually relates vector x and then the scalar. Observe that an outcome is t, but we have a scalar as what y of x. This is basically the relationship we are interested on, right? So we just recollect what we did. What to you is the training set like x1, and you have that corresponding observation t1. It is like T2 and so on, and you have this xn and then corresponding observation tn. Our interest is to get this w, so we actually are what is called the maximum likelihood estimation. In fact, the classical solution is we have to go for what is called the posterior density function of w given t, and then we have to go for the conditional median, conditional mean, conditional median, go for this conditional mode. In fact, this is what this perfect way to solve this problem, right? We are interested in getting this w, right? So here this observation, right? So this is also, let me put this as a vector to indicate that this is the observation, right? So we have this t1, t2, and so on up to this tn, right? So we are interested in getting this w, which is basically this vector, right? What the solution is, but we, as this density function is hardly available, we are trying to get a relationship, right, between this and the likelihood function. We are able to write this one as f of t given w into what? F of w whole divided by f of t. That is the way how we can write. So we actually go for this mode. In other words, this is the name maximum a posterior probability density function estimation map, in which actually we are trying to maximize this f of w given t here, right? And then right, so by maximizing this, we can actually maximize what is there in the right hand side. The denominator doesn't have w, so we are using only this numerator for optimizing that value of w. And in this, we have this f of is assumed as constant, because what does it mean is it is uniformly distributed. In that case, maximizing this f of w given t, right, is equivalent to maximizing, right, f of t given w, right? So you are trying to maximize this. This is what we call it as the likelihood function. This is called the likelihood function, right? And now for this particular problem, we are trying to get a solution for W just by maximizing this likelihood function, and hence the name maximum likelihood estimation. And we understand that maximizing this likelihood function is same as that of maximizing the logarithm of this f of t given W, as ln is the increasing function. As ln is the increasing function, maximizing this f of t given W is same as that of ln, maximizing this logarithm of, ln of f of t given W. And we have a very pakka model, right? For this t is equal to y of a, right? Y of x plus epsilon. We are able to model this one as the Gaussian, and hence we can actually find out the value of this W, which actually boils down to what is called the least square setup. Least square, right? So that is, what is that least square setup? So least square setup is something like this, what I'm going to write now. So it is going to be like matrix, right? So this is like, this is this W here. We have this right hand side as, right? So these are all these observations, T1, T2, and it goes like this all the way up to this Tn in this, and this W1, W2, they are the elements of the vector, right? So depends upon how many basis function you are going to use, right? So let us say this m here, so you are going to have the expression phi naught of x1, it is a first observation, x1 is at input, corresponding input here, and then phi 1 of the same x1 is coming here, and it goes like this, and then you have this phi 1 of, I'm sorry, phi m minus 1, right? M minus 1 of x1, right? So it is like that. And similarly, you have here phi naught of, depends upon the number of data, this is xn here, and this is going to be your phi 1 of xn, and it goes all the way up to this phi m minus 1 of xn. So this number of basis function, right, choosing and all is all the problem based. It's all more subjective, depends upon the particular problem, you have to explore it, and there is no ready-made, right, way to select this basis and all. It's all more experimental and then intuitive. So that way only you have to do it, right? So now what I want to convey at this point is this maximum likelihood estimation is same as that of your least square setup. This is the least square setup, what you see here, right? So the solution, maximum likelihood and this both are going to be the same, provided that noise is Gaussian. That is very important. Only because of this Gaussian, this maximum likelihood estimation is same as that of this least square solution. In fact, we can even directly go for this least square solution. That is one of the way, right? Least square solution can also be used directly for solving you without, right, justifying that it is coming from this maximum likelihood, right? But fortunately, maximum likelihood estimation, right, if it is least square, what does it mean? If I am using this least square solution indirectly, what actually you are assuming is the noise is Gaussian. That is the meaning of it. We can put it in that way. If I am using least square solution, you are already assuming that the additive noise is Gaussian, and then you are trying to solve this, right? So now this one we can write it in the matrix form as phi w, that is equal to t here, right? So this is this phi matrix, and this is the W vector, and this is the T vector. We are interested in estimating this W. We understood from the previous lectures that we can estimate this W using this projections, right, which we call this pseudo inverse, phi transpose phi, the whole inverse, and then phi transpose t, right? So this is going to be that, right? So this is going to be that solution for this W cap, right? So once this is known, then your model is very simple, right? You are going to have whatever the estimation we have here, right? We are going for this y of x as sorry, we are going for that W cap transpose phi of x. It is like that, right? So this is what we already discussed. Hereafter, I'm not going to write this W cap, right? I am going to use only this W, indicating that it is a proper estimated one, right? So in fact, we estimate using this, but we have to plug in here so that you will get this y of x like this, right? So this is the thing, right? So now, so someone is asking, Sivashankaran, are we going to deal with non-Gaussian distributions in this course? Yes, we'll see that also. We are going to see that. We are going for the other methods of regression, like Bayes regression, right? And then kernel smoothing, all those things we are going to discuss. That time we can understand how that is going to be related, right? But if it is non-Gaussian, the methodology is the same, right? You have to go for the likelihood function. You get an expression for it, and then you have to differentiate equal to 0 and solve for W. But the problem is the noise is right, that itself is difficult to model. It is again another parametric approach. We need to model that noise. Even if you observe this noise, we have to go for some model in that, right? Hence, that is what the reason we are ending up with neural networks, deep learning, all those things, you know. So for even for this regression problem, because the noise, the inherent noise is modeled in that automatically, right? So otherwise, if you feel that you can model that noise properly using some parametric approach, then we can actually go for the systematic way, the statistical way, that you are doing this maximum likelihood estimation to get a solution, right? So now today's class, we are going to discuss the demonstration of what we discussed in the previous class, right? So this one, so this is that the demonstration part. Here, first of all, what I'm doing here is the data generation. This part here, this part is the data generation, right? So what is the data generation here? This is for the demonstration purpose, right? So the data are also totally random, and relationship is actually collected as a random in this case, right? So you have something like W1, you have this B1 and W2, and then B2, right? So, and what is that output? Output you can see here, input into W1, right, plus this bias, right? It is like this. The model, that output is basically you are simply multiplying W1. W1 is basically that 10 cross 5 that is a matrix, and then you can say that this is H here. Let me put this as the intermediate thing here. So we are this plus we are having something like bias. I mean, this is just the data generation, right? So the size of this matrix is 10 cross 5, and of size 5 cross, and obviously this bias, right? Right. So here in this case, the bias is given as 5 cross 1, right? So it should be the other way around. So let me put it as here, like this is 10 cross 1. We have this input data as 10 cross 1, and here I mean 5 cross 10 here to satisfy this expression, and we have this B which is 5 cross 1. You have something like intermediate which is 5 cross 1, right? So you understood this thing, you know. So what I'm doing here is this X is that input data which is randomly generated. This point, this is the point where this input data is generated, which is random, which is having that range from -1 to +1, right? And the vector size, you are having 10 elements in it, right? Like x1, x2, and so on up to this x10. You have these 10 elements, that is the input here, right? So that is what this input is generated. For getting this output, we are doing it in a two stage. The first stage, you are getting a vector, which is h bar here, which is w1 into x. W1 is 5 cross 10, and x is 10 cross 1, and b is 5 cross 1, right? Like this, so that it satisfies this expression, so that this 5 cross 1. In that second stage, the output to do is you are going to use this W2 into this H. Whatever you got in the intermediate stage, to use here W2. Okay, I use this as a subscript. So W2H. Okay, so this is here we are having this one is what 5 cross 1, and your W2 is chosen as 3 cross 5, right? And your bias is chosen as 3 cross 1, and you are getting this output as 3 cross 1, right? So it should satisfy that dimension, right? So it should be like this. So 3 cross 1. What does it mean is the target vector in this case, it is not a scalar, it is a vector here. We can of course do this problem as what? The individual, right? T1, T2, T3. Basically, we are trying to find the y1 of x1, which actually gives you that first element of t, right? Using that first element of t, and then we are trying to get, just a moment, this is not x1, this is, so we are trying to find out this relationship y1 of x, and then y2 of x, and then we have here y3 of x. This is what three things. Actually, we have now three regression problem in this, right? We have three observations, T1, T2, T3. We can in fact treat this three as the individual problem and we can solve, right? So this is just a data generation. What up to this, what we have done is the data generation, right? So you can see that we are generating this data here, and remember that we have one more step in the middle to make it as a non-relationship. It's totally that linear relationship. So what we do is at this stage, we are using what is called the sigmoidal function 1 by 1 plus e power minus h. It is like that we are going to use, right? So this is the stage here. In fact, in this case, it is used h only. So let me put it as h itself. I mean, here it is like that, right? So, and even this output, we are, after getting this row, we are going to use this 1 by 1 plus e power rho. This is just to make them as a not relationship, right? I hope this is clear. This is just the data generation, right? So we got now this, have any function, I am using this function for some reason, right? You will understand reason while discussing about this neural network. In fact, this is the inherent part, it is actually the neural network, right? So we'll discuss that one later on, right? So now, as of now, this is that nonlinear relationship we are establishing between this x and t, right? So it is like the data, pure data generation, nothing else, right? So this is you can actually use the other data also to explore this demonstration. You can do that, but now we are actually using, this is the way how we are generating. So this 10 up with one observation, which is T1, right? and then x1, x2, and so on up to this x10, the same element, right, is ending up with what? The second observation T2, and then we have this x1, x2, and so on up to what? X10, right? So that is, we are going to have that observation T3, right? So like that only the data are collected, right? Now you see here, you are dividing this data into the training and testing part, right? So in this case, the training data, what we are going to have here is this noisy one, right? So we have generated 1000 data. 1000 data is actually generated, right? Out of it, 1000 data, it means that 1000 pairs, right? X and T's, like that. This is the vector, of course. We have this 1000 data collected, and we are using 700 data for constructing this W in the parametric approach, means it's for training purpose, and then we are using this 300 for testing, right? So what we do here is the testing part we are not disturbing. We are not actually, we have this input 300 collected, and the corresponding output test, we wanted this y of x, and hence I have not added it, right? Because I want to check relationship, right? So because the inherent relationship we already established, so that this output train, this is, you know, test is not having any noise. But when it comes to this training part, this is the input part and this is output, where we are adding that noise. We are adding this noise because we are saying that the observations are what? The noisy observation. I repeat, we are having the data, 700 data, which is a noisy, to mimic that it is a noisy observation. After getting this relationship, we are actually adding the noisy observation, and this 300 for testing purpose, right? Because to check it properly, we are keeping as it is without disturbing that, without adding any noise, right? So that whatever we get this result using this relation, we can compare the performance, how close it is able to construct, right? I repeat, this is that noisy observation T, output train, right? It's a noisy observation. In fact, at this juncture where you are generated this output, in fact, strictly T, they are actually that y of x. They are actually y of x. Only at this point we are actually having this T, right? This is the place where you are having actually T, because you are adding this noise in it, right? So what is available to you is 700 T's, T vector, right? You have to say that like this, because now we are having 3 elements in it, 700 T vectors, and then you have, right, 300 this vector. I will write that vector as y vectors. Y vector is basically y1 of, and then y3 of x, right? So this is y here, right? T 300 noisy observation, y of x plus noise, epsilon will come here. That is a major difference, right? So this is that noisy observation, right? We have this y2 of x plus epsilon, and then we have this y3 of x plus the noisy, right? So we, in fact, we are going to use this only for constructing this W. As you know that W is what? Phi transpose phi, the whole inverse, phi transpose T. You can in fact do this one separately, right? For, because we have 3 relationship. Let me put this one as W1 is one vector, and you have this W2 is that another vector, and 3 is that another vector. We have to use the corresponding T's to get this result, right? It is like phi transpose phi, the whole inverse, phi transpose, and you have to use this T2 here, Then of course t1 means t1 vector, right? Because you are having 700 observations in this. Don't get confused. I'm using the same notation at different place. This place it is a scalar I'm talking about, and here this t1 is a vector, right? This is the vector. I once again I will explain you if you have any doubt, right? So this is phi 1 transpose phi, the whole inverse, phi transpose, right? It is like, what does it mean? T1 vector, right? What does it mean? You have this, that observation T1, right? How many observations you have? 700. In fact, let me write it explicitly, right? To make you understand better, right? So let me write explicitly that this T1 is actually having 700 observations, like T11, T12, right? The first, and then it goes like this, and then we have here T1 700 like this, right? So it is like this, 700 elements. Similarly, for T2, you can imagine that it is T21, right? T21 and so on up to this T2 700, right? So similarly, we can go for T3, right? So this is for T2, this is for T2, and then for T3, you are going to have like 3 1 3 2 and so on up to what, 3 comma 700, right? You are actually having that vector. That is what I'm saying. This is the vector of size 700 plus 1. So like this, because 700 observations you are having, using that you are actually trying to get what is the value of this w1 w2 w3 to get a establishment of what, to establish a relationship in the regression, right? Like, you have this y1 of x, that is equal to what, w1 transpose, right, phi, right? W2 is w2 vector, I'm sorry, let me write this here, transpose phi of x, like this. And this one is what, w3 transpose phi of x, right? So we need to have this basis, right? And remember that this is the matrix, this phi is a matrix, right? Okay, so now here this is going to be that vector, right? To get that individual 1 cross 1, right? So depends upon the number of basis function what you are going to use. Now how many basis function you are going to use, and what is that basis function you are choosing in this, right? So you are actually using the kernel, Gaussian kernel based function, right? The basis function is the Gaussian basis function here, right? So what is the expression for that? Let me write. Up to this, if you have any questions, you can ask. I will clarify the doubt and then, okay. So now we are going for this Gaussian basis function. You see that the function GBF was already written, right? So that is going to take the input data, and we need this mean, and then yes, because what is that function? See, we are using the basis function phi 1, phi naught, phi 1, phi 2, and then phi 3, right? That is phi naught of x, right? So that is treated as 1 here, and then phi 1 of x, it is the Gaussian function. How we write that? It is x minus some mean transpose. Let me take this as the mean is 1, subscript 1, transpose x minus m1 by, right? This is beyond the scope of today's topic. I will explain those things later, right? So yeah, that I will do it. Divided by what? The sigma square. That is, you have this variance, right? Sigma. Let me put it as k. So the sigma is given here. So let me use the notation sigma itself here. It is like this expression, like this, and we are having this phi 2 of x, right? It is given as e power minus x minus m2 transpose x minus m2 is a vector actually, right? So it should be the vector here, right? By this is sigma 1, and here we are going to have what? Sigma 2, and then finally you have this phi 3 of x is going to be what? E power minus m transpose x minus m3 whole divided by sigma 3, right? So what we do, right, first of all, the number of basis function is arbitrarily chosen in this case, right? The number of basis function here, it is grouped as what? 4 here, right? So this is arbitrarily chosen, right? Then what we do is we are going to find out this mean. Here we that one in detail in the coming class, but I'm saying that we are using what is called the k-means algorithm to cluster the data. See, as you know, the Gaussian basis function is localized, right? So some part here, and some here. It is something like this, you know, we have different means and for the Gaussian something like this, right? So it is like that, right? It is like that. So now as it is localized to some range of input values, right? So here it is, the input values are grouped here, right? So they are localized, right? So what we do is we group the input data into 4 parts, right? So now you need not worry about how that is being done. You can imagine that there is a way to group the data, input data, into what? 4 groups based on the distance between the vectors, right? For example, if the input vector, you can imagine that this is in the space, like this, you know, this is in the space. I can use the same symbol so that you will not get confused, right? So this is the input vector. What I have drawn here on the screen is the 2D. That is the reason I am able to draw it on this. So say, for example, this is the input data, but dimensional, right? So that we cannot draw here, but you can imagine that it is in the 10-dimensional space, but 3-dimensional space only we can visualize. 10-dimensional space is difficult, you know, I mean, we cannot really visualize in this way. There are indirect way to visualize those things, right? But as of now, we are now talking to understand you. We are talking about this 2D. These are all the input data. What I'm talking, this one is this X bar. X bar is having only 2 elements. Let us say that it is like that. Actually group them. You can group them into 4 based on the between the, right? So this is like group 1 here, and we have here group 2, and then we have here group 3, and then we have here group 4, right? And we can actually find out the average of these groups, right? So that one we can call it as mean vector m1, and we have this m2, and then we have this m3, and then m4. In fact, we can find out that variance of this individual data at maximum variance in it, because this is a 2D, so we can actually find out the variance for the individual element, right? So in other words, this can be modeled as like a ellipse, right? We can have it as like this because it's a mean, right? So we can actually find out how far that major axis in it, right? So it is basically that we have only 2 variants. We have the major axis and the minor axis will be there, estimate of that variance. In that case, we can go for the maximum in it. These are all intuitive. Whatever I'm saying, they're all, this is not the only way to attack this problem, right? What is more important is how the regression is able to get a solution. That is what I'm demonstrating. K-means algorithm is out of scope as far as this class is considered, right? You are going to do that. The point is, what I would like to convey here is you are actually grouping them into 4 and then finding out this mean for the individual, right? And that is being used in the basis function. That is what I want to convey. Because you may wonder, right, how to fix this mean vector of the basis function and then how to fix that variance of that, right? So one way to attack this problem is group them into 4 groups, right? And this 4 is also arbitrarily chosen, right? So this 4 is also arbitrarily chosen. You can actually explore for 5, 6 and all, right? But this experiment, what I am going to demonstrate today, right? The number of basis functions are going to be, I mean, we are going to divide that one into 4 groups, right? So it is like that. Now you are actually constructing, this is the way how we can find out the variance for that individual basis function, right? Now you are going to construct matrix and then you are going to find out the w's in each case, right? So the GBF is the function already written by myself. I mean, that will actually return back the basis functional value. It is like if you give me the vector and then mean and then yes, right? This is the function, right? So you have a function which is called GBF, right? In which if I give this x and m and s, it will directly give you e power x minus m transpose into what? X minus m. This is a, in this case, it is a scalar quantity, yes. This will return back actually this, right? So that is that GBF function which is written here. So you are collecting one by one and then you are constructing that matrix, right? So it is like that. You see that the matrix is constructed like this, then right, like, you know, have this phi naught of x1, phi of x1, and then phi. In fact, I can now write how many are there. We are having 5, phi 2, then phi 3, then phi 4. It is like that. And it is identically chosen that the first basis function, the value is 1, right? I'll tell you the reason for this one. This is acting like, as how you can consider that the first basis function is identically equal to 1 here. So this is phi naught of the number of data. The number of data what we are using here is 700. So it is going to be that 700 thing. And then here we are going to have that last element. Of course, I can write that also. Phi 1 of x 700 and then phi 2 and so on to this phi 4 of x 700, because we have that 700 element in it, right? So this is going to be that 700 cross phi matrix, right? So your w vector, you are going to have only that phi element, w0, w1, w2, w3 and then w4, right? So you are going to find out the w in this, right? So the w is going to be what? You are considering this matrix and then phi transpose phi, the whole inverse, phi transpose t, right? Remember that you have here 700 cross 1, right? So this will end up with what? Phi cross 700, and hence your w vector is going to be what? Phi cross 1, right? So now you, after getting this w, as I told you, I will not write cap. Let me put this as w itself for writing purpose, right? So you once you get this w, in fact we do this job, right, for every t's, right? So because this problem expecting 3 regression problem, right? So in fact for this t1, if you substitute, you get this w1. If I put t2, you get w2. If I put t3, you get w3. If I use that matrix right? And then you are going to get a solution for it using this pseudo inverse, right? You can see that the value W, how it is estimated using pseudo inverse. This is the matrix for the training data, and there is an inbuilt function in MATLAB which is PINV, which is exactly doing the pseudo inverse of this matrix, right? It will do this and then multiplying with what? T here. Pseudo inverse is PINV, right? It is a pseudo inverse. Pseudo inverse of this matrix and multiply with this T, you get this W. And I am saving this, and then for testing purpose, right? For testing purpose, the original value, you know what is that? Because we already had this Y's is the original value. But now using these W's, we are going to model them as Y as what? Yes, W transpose, W1 transpose, for example, the first T is into what? Phi of X. And remember that this phi is a vector. So I'm using many places phi and all. You have to be very careful. In this case, it is a matrix. I'm not able to draw it boldly here, right? So that is the reason I'm saying orally that this is a vector here. So you can actually understand based on the dimension matching, right? This phi, what I'm writing here is actually phi naught of X. X phi 3 of X and then 4 of X. In fact, the first element is 1. That is what we are having this. The whole first column is going to be 1. And then once you get this W, we are trying to get the result. We know the result, right? But in this case, we are using this W1 transpose phi of X to get this output, right? So now we are going to check that how these two are close to each other, right? We'll see this result first and then we'll continue, right? So other things I'll show you little later. Only this result I just wanted to show now. I hope you are able to see. Are you able to see the screen what I am sharing? Yes, okay, fine, good. So here, this is the input data. What you see here is the input data, right? So what does it mean? It is actually the representing the data, right, in a image format, right? As you see here, this one, right? This 1, 2, 3, 4, 5, 6, 7. Input, in that analysis, they are going to be that size of 10 cross 1. I hope this is clear, right? Every column is the data, right? So how many data you have now? The number of data in this one is 700. You can see that there are 700 data. This is what we call it as the training data. The training data is having now okay, you have this 700 data, right? So these are all the training data. And what you see here, right? This one is the output. Y1, Y2, Y3, they are all the output here. And this is the original, and after adding noise, you have some disturbance in it. The variance of the noise is made it as small. You are not able to see it more difference, but this is the output, right? So this is the first output, second output, third output, and this is all the 10 inputs. So this is another way how we can actually show the figure, I mean the data, right? Now you can see this is the plot now. What you see here is a plot. They are all the input data, 10 data, right? But they are all the testing data because I have 300 here. You can, I hope you are able number 300, what I am showing you, right? So this 300, are you able to see that arrow? Whatever is able to see, right? So this arrow you are able to see, isn't it? Yeah. So that so this is what, right? 300 data you have, right? And now 10 different input, 300 data, what you see here, right? And what you have to see now is the regression. This is what you have to closely watch, that what is that original and what is that that model, what you are able to get. You see that this blue color is that original for this 300 data, which is the testing, and what you got this red, it is basic model. You have to see how close it is able to track the shape. Very important what you are seeing now. It's very interesting to see the strength of regression using this linear, right? Model. Actually, right? You can see that 3 different models, right? So for y1 of x, y2 of x, and y3 of x. Very important. This is for the testing data. If you are plotting that graph for the training data, still get a pakka overlapping. You will get a proper, one merging with each other almost. This is for the testing data. You have to be, you have to appreciate that how close it is able to track it, right? That ups and downs, whenever the peak is coming, and you are able to predict that there is a peak in it. When there is a down there, and you are able to predict that it is down, and it is able to track the pattern, and that is that regression model, right? What we really achieve, right? Of course, it is a synthetic data what we got, but the theoretically this is what we are achieving, right? This is what the demonstration is, right? So we developed the nonlinear relationship, and we purposely made it as a noisy observation, adding noise in it, and then we tried the regression model, and then we see how close it is, right, with that original data, and we understand that it is able to track it properly, right? So we can actually show this one, right? This is fourth, right? In image also, you can see that this is the original, and this is the what the model is giving. This is the data. This is for the testing part. Whatever you see at the top, they are all the input we have, and then we have this output. 1, 2, 3. They are all the output, and we have this corresponding observation here. I mean estimation here, right? So this is this whatever you see in the third row, they are all the estimated one using this regression. This is the original, and this is the, and you can see almost it is able to track it. I mean, at least the shades are the same. You can see that the top shade, and here the top shade is light, and then you have this middle one, and here also this middle black, and this all, right? So you are able to get it properly by using this regression model, right? So we will stop here. I think if you have any questions, I would like to answer before proceeding.